Alright folks, we're going to try something new today. I'm going to test out some technology. This app that I'm using is called Explain Everything. It's pretty good. I might get you guys to maybe use it for maybe an A-level stuff coming up pretty soon. Anywho, I want to go over a few things. I hope everybody liked the little TED Ed video about static electricity. Most of that stuff should be a review, so we're not necessarily going to go over that too much unless anybody has any specific questions. So we're just going to jump right into the stuff that is probably brand new to you, which has to do about electrical current, voltage, and resistance. So first of all, what is electrical current? So electrical current is defined by the continuous flow of electrons, electrical charges, let's say from point A to point B. Okay? Current, as we call it, is measured in the unit of measurement called amperes, all right, or amps for short, and we abbreviate that with the capital A. Okay, so amperes was a French scientist who is named after. Okay, but there are two guys who are the titans of electricity, which we're going to talk about a little bit later, who focused on these next two components, alternating current and direct current. Okay, so back when the world was becoming electrified and the infrastructure around the world was starting to be built, there was a debate on which type of electrical current was the best to use. Some people were proponents of what we call direct current down here at the bottom. As you can see, direct current, just as the name insinuates, follows a direct path. Charges flow only in one direction, and they can make a loop, so to speak. So here in the flashlight, you can see that when the electrons are, when you line the batteries up according to positive and negative, the electricity will flow in this continuous loop here. Okay, so people that were proponents of direct current were mostly funded by some guy named Thomas Edison. You probably heard of him. So the alternate, shall we say, perspective of how we should wire the world was headed up by Nikola Tesla. He was the person who was fundamental in the development of what we call alternating current, or AC for short. Now, alternating current had a lot of advantages over direct current. It could travel over long distances without losing as much of the energy, so to speak. Okay, so alternating current, literally flow of electrons that regularly reverse direction. Okay, all right, we'll get into that more a little bit later. All right, so as a review, we talked about this back in the chemistry unit, what causes things to be electrical conductors and what causes things to be electrical insulators. Now, if you remember, the types of substances that are good conductors happen to be metals, all right, and mostly the transition metals, the one located in the middle of the periodic table. Okay, now remember, the reason why that is because that you have these groups of electrons right here that do not necessarily have a fixed electron orbital. We call these the electrons that were in the sea of electrons. Okay, these are the ones that are free to move around. Since they're not fixed in any particular positions, they can move quite easily. Okay, so electrical insulators, are types of materials that are opposites. These happen to be mostly covalently bonded materials. So your plastics, your rubbers, these sorts of things. These types of materials do not allow electrons to flow very easily because the electrons are bound more tightly together. All right. So when we're looking at electrical circuitry, both of these are really important. We need materials that are good conductors and we need materials that are good insulators, okay? So I want you to think about why that is, and we're going to come back to that here in the next couple of days. All right, so another big concept that we have to go over is the concept of resistance, okay? Just like what this word means in English, when you oppose something, resistance is the opposition of the movement of charges flowing through a material, okay? Now, different materials are made up of different stuff. Some of them are mixtures, some of them are pure substances, okay? As an electrical charge travels through any material, it's going to come in contact with the particles, shall we say, right? And how much it comes in contact with those particles, we refer to that as the resistance, okay? Now there's three factors that affect resistance, okay? Thickness, length, and temperature, okay? So thickness, length, and temperature. So the diameter and length of a wire also affects the resistance of the circuit too. So thickness, okay? Thick wires thick wires tend to have less resistance because there's more space for the electrons to flow through, okay? The length of the wire usually affects the resistance in a negative way. The longer the wire, the more resistance it has, okay? And this is because it has to travel through a longer distance and has more opportunities to come in contact with that different material. So therefore, the more it comes in contact, you can think of it like friction, so to speak, okay? And so the more it comes in contact, the less is going to make it out the other end, okay? And so I want you to think also about why do you think that is? What did we learn about the atom specifically that could probably cause this problem? I want you to think about that too, okay? Temperature is also a factor too. You can probably relate to this with your laptops, right? Temperature is high temperature is the enemy of electrical devices, right? So is low temperature. So anytime those particles are moving around really, really fast or really slow, okay, this can affect how easily the electrons are moving through the material, okay? So the next part we get into here is voltage, okay? All right, so there's three things that we're going to be going over today, specifically when it comes to how to make these calculations we're going to teach you today. The first concept is voltage. Okay, you probably have all seen one of these signs before around your neighborhood, maybe in your apartment building, right? These high voltage signs. Now, what voltage literally means is electrical potential, okay? Just, you know what that word potential means, right? It's the ability to do something. So anytime you have a buildup of electrical charges, there is a potential for them to move from point A to point B, okay? This is why you don't want to go around high voltage objects because they have a lot of electrical charges that are stored, right? And if you have a very few electrical charges on you, let's say static electricity wise, right? If you come in contact with that, the potential for it to move is very high because you have a high concentration in one place and a low concentration in another. So therefore, if you get really close to it, it might actually electrocute you. So you have to be really careful. Okay, so voltage, like we said, is technically potential difference. It's the difference between the different objects and how many electrons that they have on them. Okay, so voltage was discovered by an Italian fellow named Volta. Okay, now the volt is the thing that we're measuring. Okay, and so we represent that with the capital V. Okay, now the unit of measurement when we make our calculations, we measure these in what we call volts, and we express that with a lowercase v. Okay? So, voltage causes current to flow in an electrical circuit. You cannot have an electrical circuit unless you have an energy source, okay, or a voltage source. So voltage sources are things that create this potential difference in electrical circuit. So examples of these are batteries, right? We know batteries are highly concentrated areas of electrical charges, right? And also for generators. So these two things are examples of things that we consider voltage sources. Okay, the next thing we got here is resistance. Now resistance is expressed with a capital R. Okay, now a resistor uses electrical energy as it interferes with or resists the flow of electrical charges. Anything that uses electricity is technically a resistor, okay, because if an electrical current goes through that object and it uses that and converts it into some other type of thing, okay, whether it be sound or whether it be light or whatever, all right, it's technically slowing down in this process, okay, and we would call it a resistor. Now, resistance, capital R, is measured in a unit called ohms, named after a German fellow as well, who came up with this whole concept. Now, ohms is measured in the Greek letter omega, and it looks like an upside down horseshoe, okay? Maybe a little hard to draw for you. I know it is for me. But anyway, so ohms is a measurement of resistance. So, the greater the resistance, the less current there is for a given voltage. So, if you've ever plugged up several different devices into the same power strip, you probably experienced this. It sometimes dims, and so there's too many things using electricity in one particular place. You're increasing the resistance so much, so it takes away from all of them. Okay, so current depends on the resistance offered by the material through which it travels through. Okay, so different materials have different amount of resistance. Okay, so the best conductors have the least resistance. So silver, for instance, is the best conductor of electricity, so therefore it would have the least amount of resistance, okay, than other pure elements. Okay, so like we said earlier, the resistance of a wire depends on the thickness and the length of the wires. Long wires have more resistance than short wires. Thin wires have more resistance than thick wires. Okay, think about it. Thin wires have very, very, very narrow pathways for the electricity to flow through. So if you have a high voltage, if you have a whole bunch of electrons wanting to move from point A to point B, and there's only a small strip of area for them to travel through, it's going to create, shall we say, like a traffic jam, right? You got a lot of cars on the street trying to go down a one-way street. It backs things up, slows the whole process down. Same principle, okay? So now we're going to get into the concept of how to make some of these calculations. Anytime an electrician comes through and gets ready to set up the electrical outlets in a house, they have to go through this process that we're doing here, literally. Okay, Ohms was the German fellow who came up with this concept, and he noticed there's a mathematical relationship between voltage, current, and resistance. Okay, so here we have the Ohms triangle here. As you can see, the Ohms triangle is set up to show the relationship between these things. Okay, so voltage divided by, voltage is equal to, current, which is expressed with the letter I. Okay, resistant times resistance, which is expressed with the letter R. Okay, now these are the things these are the letters that represent these particular things. Okay, so over here, be sure you pay close attention to these parts. Okay, voltage, capital V, is measured in volts, lowercase v. Current, capital I, is how we represent that, is measured in amps, or capital A. Resistance, capital R, is measured in ohms with the omega sign. Okay? So let's say we want to solve for V. So what we, just like we've been doing in the past, we have our little triangle. All right. Pardon my ugly handwriting here. I'm trying to write on this iPad with this stylus, and it's kind of awkward. So bear with me. So let's see. So if let's say we have a very small circuit, like one in your computer, and it has a voltage of 0.2 amps, all right, and it goes through a resistor that has 30 ohms. Okay, so how can we solve for voltage? Okay, so for voltage, we first, step one, right, is we go through and set up our equation, which is V equals, we look at our triangle, it's I multiplied times R. Okay, so that's step one. All right, so step two is we're still solving for V, so we put our V there. So we substitute our variables in with the appropriate units of measurement. So like I said, 0.2 amps, all right, and we multiply that times 30 ohms. All right, that wasn't too bad. All right, so step three is we substitute, after we substitute, we solve and show the appropriate units. So if we multiply 0.2 amps times 30 ohms, that gives us, all right, 6 volts. Okay, so this is an example of how to solve for voltage. Okay, now let's do another one. Let's do one here where we are solving for current. So remember, current is expressed the letter capital I. And if we look at our little diagram over here, remember, current is equal to voltage divided by resistance. Voltage is capital V, resistance is capital R. Now let's say we're going to solve for I. So let's say we have, we know how much voltage our battery has, and we know how much resistance one of our resistors has, and we want to find the amps that's going to be able to go through it, the current, excuse me. So let's say if we have a 1.5 volt battery, and we have a resistor that is 15 ohms, right? How much current does that have? So how much current can flow through this particular circuit? So 1.5 volts divided by 15 ohms, is 0.1 amps. Okay? So remember, current is expressed with a capital I, but is measured in amps. Okay, you can write it out the full way, or you can say just an A, abbreviate with an A. Either way is fine. Okay, and last but not least, let's solve one for resistance. So if we look at resistance, resistance is capital V over V over I, right? Okay, very good. So we're going to solve for resistance here. So let's say we know that we have, let's say, 3.0 volts in a battery, okay? And let's say we have a circuit that is designed to use 0.10 amps, okay? So we want to know how much the resistors are experiencing there. So capital R is going to be equal to 3 volts divided by 0.1 amps. That gives us a total of 30 ohms. Okay, so that's how we make those calculations. So remember, follow the 3 steps, and also remember the letters that represent the 3 parts of Ohm's law are different than the letters that we use to write the units. Okay, so pay real close attention to that. All right, so now if you go online and take the little quiz, you have 10 problems to do for Ohm's law. Do those, and I'll check those as soon as you get them in. Thank you.